In this video, we're going to talk about solving systems of equations in three variables. Before we do that, let's review systems of equations in two variables, and then we move on to solving systems with three variables. There are three methods, earlier methods, that you probably were exposed to in the previous course, elementary algebra. And those methods were, for solving system, were graphical method. You should know or have heard about the elimination method, and you should also know about the substitution method. So those are the three methods that you already have exposure to, and you know about solving systems of two equations. Now, we're not going to be doing the graphical method in this course because you've done that earlier. But just to give you a little bit about the graphical method, when you use graphical method and you graph two lines, a number of things could have happened. So, for example, you could have two lines, two crossing lines, and in that case, the point of intersection is the solution to the system. So here I have x1, y1 marked, and this is where the solution is. The system, in this case, is called a consistent system. That means it has at least one solution. The other thing that could happen when you graph two lines is that, for instance, it could be that the two lines become parallel lines. So these are, let's say, two parallel lines I have. Okay, and there you go. So these two parallel lines now, let me draw this a little better. This one. So I have two parallel lines, and in this case, because there is no point of intersection, therefore this is a system that has no solution, and the system is called inconsistent. Okay, now the last thing that could happen when you draw any two lines is that the two lines could actually be the same lines. So for instance, I have a line here, and then I have this second line that overlays on top of this one. So in that case, I have two overlapping lines. And when that is the case, then the system again is consistent, but more specifically, we call that a dependent system, and it has infinite solution. Okay, so those are the three things that could happen in the graphical situation. Now, let's take a look at the idea of elimination or substitution here. So, for instance, let's say I want to solve a system. Okay, in this system that I have, let's say an example. In the system is, let's say 2x negative y is equal to 4, and the other one is 5x negative y equal 13. Okay, and I want to solve this system using both elimination and substitution method, two different methods. Okay, so let's take a look at first the substitution method. So in the substitution method, we have a choice of the variable to choose from, and we have the choice of the equation to choose from here. So let's say in the first equation, I choose to solve for y. Okay, so that is in this equation. I want to solve for y. So I have negative y. That means isolated. So negative y is equal to 4 minus 2x, right? Moving 2x to the other side becomes negative. And then if I multiply both sides by negative 1, that would solve it for y. And there you go. So I multiply by a negative, and the 4 here becomes negative 4, and then negative 2x becomes positive 2x. Okay. Okay, and then what I need to do next is to substitute for y in the other equation. Okay, so that's what we're going to do. We're going to move y and substitute it right in here. Okay, and when we do, this is going to become 5x negative y, but then remember, y is 2x minus 4, so I'm going to put 2x minus 4 here for y. Okay, and that is equal to 13. And then we're going to remove parentheses, so this is going to be negative 2x plus 4, you distribute the negative to both 2x and negative 4, equal 13. And then next step, combine like terms, 5x and 2x, negative 2x that is, makes 3x plus 4 equal 13. And then subtract 4 from both sides. This becomes 3x equals 9. And finally divide by 3. And we solve for x. Okay, now once we've solved for x, we can actually now back substitute for x, which is a 3 in the other equation. So doing so will give us the solution to y. And that's what I'm doing now. So this is going to be 2 times x is 3 minus 4. That's 6 minus 4, or 2. So we have the solution. The solution is always in the form x comma y, the ordered pair. So the solution in this case is 3 comma 2. Again, note, if you write 2 comma 3, that is an incorrect answer. That would imply x is 2 and y is 3. So we got to keep the order in check here. Okay, so there you go. That's how the substitution works. Now let's solve the same system using the elimination method. Okay, now by elimination method, that's what I'm doing now. Elimination method. So for elimination method, now what we do is we actually have to choose a variable in the equation to get rid of or to solve for. Okay, now which variable you want to eliminate depends on the coefficients on x and y. So in this case, in this case, there you go. Because the coefficient on x, the 2 and the 5 are different, it's easier to get rid of the y's in this case. Notice they just need to become opposites in order for them to add to 0. So I'm going to multiply the first equation by negative 1. Okay, so this is what I'm going to get. This is 2x negative y equal 4. I'm just rewriting the system at this point. And if I multiply the first equation by negative 1 times the first equation, it's going to become negative 2x, right? Negative 2x plus y equals negative 4. And then what I can do is I can add it to the second equation. And as you can see, y's are now opposite in sign, right? They have opposite signs. One is positive, one negative. Next, I'm adding the two equations together. So this is going to make it 5x and 2x. And that makes 3x equals to 13 minus 4 is 9. And then divide both sides by 3 and x becomes 3. Note, of course, we have the solution already. We don't expect a different solution, right? The solution doesn't change. It's just the way we go about solving it is changing. Now, once you solve for one of the variables, the next step is just like the substitution method. I can substitute for x in the other equation. I can put it in either equation, in fact, and it will work. So that's what I'm going to do next. Plug in 5 times 3 minus y is 13. 5 times 3 is 12 minus y is 13, and negative y is 5 times 3, sorry, is, I know it's not 12, it's 15. And subtract 15 from both sides, we get negative 2, which means y must be 2. So you can see again, we got the exact same solutions as we did before. So this is what, again, you were supposed to have learned coming into this course. And section 8.3, of course, are applications. Now, our focus, so we're going to begin actually looking at a situation where we have 3 equations and 3 unknowns now. Okay, so now that we saw this example with 2 equations, 2 unknowns, we're going to extend the same ideas to 3 equations and 3 unknowns. So here's a possibility with 3 linear equations and 3 unknowns. Each of those equations in x, y, and now we'll be adding a z to it, a third variable z. If we graph each of those linear equations, the resulting graph is going to be a flat surface. Now with 3 equations, there are going to be 3 surfaces. That's why in each of these drawings, in these sketches, you'll see 3 planes here, for example. You will see 3 here. Those are actually 3 planes crossing right here along the side of this line. And you have 3 planes coming together at the corner point, and so on. These two, of course, are repetition. Here you have all 3 planes that coincides. In this one, you have 2 planes that coincide parallel with a 3rd plane. So as you can see, a number of things, a number of situations could happen. The one that has only one solution is this one, the first one. The rest of them either have infinite or no solution. So right in here, infinite solution, this one next to it, because every point along this solid line will be a solution, and there's infinitely many of those. Keep in mind, these planes, each of these extend indefinitely in all directions. So this is just a snapshot of an infinite surface. Here we have 3 parallel planes or surfaces. These do not cross at a common point, neither at a single point or a common line or a common surface. Therefore, this one has no solution. This one doesn't have a solution either, because they're pairwise solutions. So these two, I guess, come together, so we can find solutions that work in these 2 equations, but not in this one. Here you can find solutions that work in this for these 2 surfaces, and by surfaces I'm talking about this one and this one. Everything here will work in both, but then it's not going to work in this plane and this one. So that one does not have a solution either. Okay, and let's see here. You have a dependent system, infinitely many solutions here. Okay, because every point that you take falls on all 3 planes. So this one has infinite solution. The system again is consistent and dependent, and so on and so forth. So let's actually take a look and see how we're going to solve a system using 3 equations and 3 unknowns. So here's a typical system of 3 equations, what's going to look like. So let's actually take a look at, we're going to look at the substitution method. Now don't worry about the graphical method. In this course, again, we're not going to use graphical method to solve the systems, because we don't know how to plot points in 3 dimensions, and that's not how it's done anyways for 3 or higher order systems. Beyond 3 equations, 3 unknowns, we cannot even graph these in a 3-dimensional space. So graphical method of solving system definitely has its limitations. So let's take a look at substitution. Now, using substitution method, again, I have 3 equations here to choose from. Okay, so I have this equation, this one, and this one to choose from, and I have 3 variables to choose from, right? Any one of those. So I got quite a few choices to make here. Okay, now what I need to do is I need to pick the easiest variable to solve for. And this is such an easy system. Looks like the first equation to me seems to be the easiest equation to solve for, right? This one. That's the easiest one to solve for. And it doesn't really matter x, y, z. See, anyone that has a coefficient of 1 means a number times x, y, z that is 1 would work. So I'm going to solve for x, okay, in the first equation. That means I'm going to keep x and move y and z to the other sides. And there we have. So I've solved that equation for x. And then once I have that, I'm going to substitute for x in the second equation. So substituting for x in the second equation becomes 4 minus y minus z, right? That's what x is. Negative 2y, negative z equal 1. And then I can combine like terms. I get negative 3y, negative 2z. Subtract 4 from both sides, and I get negative 3. Okay. Now, if I multiply everything by negative, just to get rid of all the negatives, this is going to look a little nicer. That's 3y plus 2z equals 3. Okay, so I'm going to put that aside. Now, next time, I'm going to substitute for x in this equation now, in this third equation. And doing so now is going to give me 2 times x, but remember, x is 4 minus y minus z, right? That's the substitution for x leads to negative y minus 2z equals negative 1. And then I'm going to distribute the 2 over. 2 times 4 is 8. 2 times y is 2y. Negative 2z minus y minus 2z equals negative 1. Okay. Now, combine like terms, and I get negative 2y, negative y makes, I'm combining these two, and that's going to give me negative 3y. The z's, that's, I got negative 2z here, negative 2z makes negative 4z's. And finally, I can subtract 8 from both sides. That makes it, see, like negative 8 makes it negative 9 on the other side. Okay, so that's how I can work this. And next, I'm gonna, just like I did up in above that, I'm gonna multiply everything by negative. That's just to make everything with a positive coefficient, and there I have this new equation. Okay, and there's my 9. Now, once I have these two equations, I'm gonna pair these two together. So in effect, what we did is we reduced the system from 3 equations, 3 unknowns, down to 2 equations and 2 unknowns. So this is 3y plus 2z equals 3. What I'm doing now is I'm pairing them together. That's all I'm doing. 4z equals 9. And there. Now this new system, I can solve it again by substitution, elimination, whatever works. So I'm going to use, actually at this point, because elimination is easier to do this one. Instead of substitution, I'm going to actually do elimination method. So let's say I want to get rid of the y. In order to get rid of the y, I'm going to multiply the first equation by negative 1. Okay, doing so will make it negative 3y. Negative 2z equals negative 3. Then we have 3y plus 4z equals 9. And then I'm going to add them together, adding them together. Those two add to 0. And then I have 2z equals 6. Divide by 2, and that will solve for z. So z is equal to 3. Okay. So that's what z is, equal to 3. And then once we have solved for z, we can now back substitute into, I'm going to back substitute either in here, or you can also back substitute into, say, this one, or you can go into this one. Okay, either one would work. Either would work. So I'm going to actually go ahead and substitute into which one is easier. Maybe the first one is just a tad easier. Smaller numbers are easier. That's what we mean. So I'm going actually up here, okay, and substituting in there. Okay, so this is going to make it 3y and plus 2z, but then z is 3, correct? So that's times 3 equals 3, and then solve for y. 3y plus 6 equals 3. Subtract 6 from both sides, and that makes 3y equals negative 3, and hence y is negative 1. If you divide both sides by 3, that's what you're going to get. Now, once we have solved for y and z, if you look at the first equation that we had, which one? This one. Look at that one. That one will solve for x. So I'm going in that one to solve for x. X is 4 minus y minus z. true, x4 minus y minus z. And then I can substitute for y at -1 and for z a 3 minus 3. And this will give me 5 minus 3, and that's going to be a 2. Okay, so x is equal to 2, and that will solve the system. The solution is now in the form of x comma y comma z. Usually it's alphabetical, so if the variables are a, b, c, you write them in that order. If they're w, x, y, you write them in the alphabetical order. So it's going to be 2, -1, and 3. Okay, and there we have that one. So we were able to solve this system. Okay. Now, if the system is dependent, or let's say the system is inconsistent, what's going to happen is along the way, let's say you're going to get into a situation where you get a false equation. The variable disappears and you get a false equation indicating the system is inconsistent and has no solution. So let me give you an example of a system that is actually inconsistent and has no solution. So take a look at another example together. So here I have x plus y plus z equals 0, and then 2x plus 3y plus 2z equals -3. And -x, -2y minus z, let's say that's equal to 1. And we want to solve this again by substitution. So like before, I'm going to solve for, and let's say I want to solve for y this time, just to be different. Move x and z to the other side, or subtract them from both sides. And then what I'm going to do is I'm going to substitute for y in here and substitute for y in here. Okay, that's what we're going to do next, substitution. And when I substitute in the second equation, it's going to be twice x is of plus 3, and then y is -x minus z. Okay, -2z equal -3. And then let's simplify this. 2x -3x -3z minus 2z equals -3. Combine like terms, we get -x, -5z equals -3. And again, if I multiply everything by negative, x plus 5z equals 3. You don't always have to do that. It's just so far. If everything is negative, I usually do that. But if one of them is positive, then forget it. Or usually if x and even if these two negatives are one negative, one positive, you leave it alone. Okay, so usually when they're both negative, I do that. Okay, so I substitute in a second equation. Now I'm going to substitute for y in the third equation. So in the third equation, now that's -x, negative twice y, but then y is -x minus z. And then -z equals 1. Let's distribute. We get positive 2x plus 2z minus z equal 1. And then let's combine like terms here. So we get x plus z equals 1. And this one is already in a nice form like that one. So here is when we actually now have two equations, two unknowns. So let's say we want to use elimination to get rid of this one. X plus 5z equal 3, x plus z equal 1. And let's see, for this one I want to make sure I copy the problem right. So x plus y plus z 0, 2x plus 3y plus 2z. Let's shoot it. Let me Actually, I didn't copy one of the problems right. So let me actually do this. Let me pause this and fix this up. Okay, so let's take a look at this system now. We're going to try to solve this system again, this system by the substitution method. So I'm going to solve for x in the first equation, moving y and z to the other side, or you can subtract it from both sides. So that's what x is. And then we're going to substitute for x, plugging back into these two, right? And that's what we're going to do. So plugging it into the first one, first of all. That one is going to give me 2 times x, but then remember x is negative y minus z, right? That's what x is. So I plugged it in. Plus 3y plus 2z equals negative 3. Distribute over from 2 to distribute 2 to y and z, we get negative 2y, negative 2z, plus 3y plus 2z equals negative 3. Negative 2y and 3y makes y. The z's actually add to 0, and we can substitute for y. It seems like we have a solution for y. Okay, and then let's substitute for x now in this equation and see what happens. So here we're going to get negative of x, but x is negative y minus z. Okay, and then negative, oops, sorry, I didn't have the right color here, negative 2y, negative z equal 1, and this distribute makes it y plus z, negative 2y minus z equal 1. Combine like terms, and this will give me negative y is equal to 1, which means y is negative 1. Now check this out. So in this case, we got 2 different solutions actually, right, when we plug them in. So this is the sign that the system is an inconsistent system. So this system, that can happen. Therefore, this system is inconsistent and has no solution. Again, there's nothing we did wrong. It's just the way this was developed. All I did was subtracted y and z from both sides, substituted into this equation, right, the first time. I got 2 times negative y minus z plus 3y plus 2z equal negative 3. Distributed the 2 and combined like terms, so y turned out to be negative 3. And when I substituted into the third equation, I got a different answer, right? So there's nothing we did wrong here. So this one has no solution as a result. Okay, so the point being, there's no solution. Inconsistent, therefore no solution. Okay, so usually something goes wrong when you try to do this. Let's say a system that is dependent, what is it gonna look like? So let me make up again this example, and let me put it on there, and we'll solve another system that's dependent. Okay, so let's actually solve this system now. I'm gonna use substitution method. This time I'm gonna choose the second equation actually to solve for x, because it's easier to solve for. Therefore, I'm going to move 6y to the other side and 3z to the other side. When you move things from one side of the equation to the other side, we change the sign on those. Our first equation is negative 2x. I'm going to back substitute in our first equation. That's going to be negative 2, and then we're going to plug in for x, right? So it's going to be 4, negative 6y, negative 3z. That's what x is. Plus 8y plus 2z equals 4. And distribute, we get negative 8, positive 12y, positive 6z plus 8y plus 2z equals 4. Then we're going to combine like terms. So here I'm going to get 12 and 8. That makes it 20y. The z's, 2 and 6 made 8 z's. Add 8 to both sides, we get 12. Now notice this time everything is divisible by 4. So I'm going to divide everything throughout by 4. I get 5y plus 2z equal 3. And there we have it. So we have this is actually an equation with two variables, right? With just y and z. Now, what we're going to do is we're going to substitute instead of, remember I substituted just now in the first equation. Now what we want to do is we're going to substitute for x in the third equation. So now it's going to become 3 times in the third equation x. X is 4 negative 6y minus 3z. Okay. And negative 2y plus z equals 0. So what do I need to do now? Let me distribute, right? 3 times 4, 12. Negative 18y, negative 9z, negative 2y plus z equals 0. And then I'm going to combine like terms. The y's are like terms. Combined, I have 20 of those. And again, z's are like terms. Negative 8z. And subtract 12 from both sides. I get negative 12. So you move it over to the other side. Okay, so hopefully you followed all of that. And then multiply everything by negative. And actually, again, just like the one above, in fact, look at these two equations. They're identical, aren't they? So that is the sign we have a dependent system. So let me divide everything by negative 4 this time. By negative 4. So I'm going by negative 4, by negative 4, by negative 4. That's what I'm going to do in a moment. Okay. And when we do that, we're going to get 5y plus 2z equal 3. Now, again, if you look at these two, they are identical. Okay, so this is the sign that the system is a dependent system. Dependent system, therefore this one has infinite solutions. Okay. Infinite solutions. And it's like, well, how do you find one solution? Okay, how do you find one solution? You can just pick a random number. So this is just, let me call this extra, because your book doesn't do it. You're not required to do this. Call it extra stuff. So I'm just going to pick an easy number. Let z be 0. You can pick z, y, doesn't matter. Be any number. If z is 0, then 5y plus 2 times 0 is 3, 5y is 3, and y is 3/5, which is a fraction, but that's okay. So there you go. When z is 0, y is 3/5, and then you can back substitute in the original system up here for y and z, and then solve for x, which I'm not going to do. Okay, so anyway, just to point out that it is possible to get a solution that way. Okay, so there you have it. We just went through substitution method for solving a system, right? Now, the same system that we just did, that we have a solution for this one. Let's redo this system. Let's redo it using the elimination method. Okay, so that's what we're going to do next. We're going to solve that system by elimination method. Okay, so here's the system again. I just wrote it down. And we want to solve this system by the elimination method. Okay, that's what we want to do. The elimination method. Now, using elimination method. So here's how this method is different from the substitution method. Initially, with 3 equations. What we need to do is we need to pair these equations together. So as far as pairing goes, I can pair first and second one together. You can pair first and third one together. And you can pair second and third together. So there are 3 possible pairings of these. Okay. Now, how we pair them depends on, again, which variable we choose to eliminate. So looking at the system, you choose the variable that's easiest to get rid of. In this case, again, the system any of them are good to eliminate, x, y, or z. If you look at here, for example, we got x and x. All it takes for these to be opposites and x is eliminated. If you pair, let's say, first or second with the third one, you can easily eliminate x by creating a -2 in one of these. And the same thing with y and z. So let's say I want to get rid of the z's. Look at these two are already opposites, easily eliminatable. Okay, so that's what I'm going to do. I'm going to eliminate z's because I see opposites in here. Okay, so in order to do that, so I need to do my pairings first, right? So here's my first pair. It's going to be x plus y plus z equals 4, and then x -2y minus z equals 1. That's my first pair. And I want to get rid of z's. All I have to do is just add these two equations together. That's one of the properties of systems, right? We can add equations together in a system. So when we do, those z's add to 0 and we get 2x -y equals 5. So here's one equation. Now, I need to create another pairing. This other pair I'm going to do, again, keep an eye on z. We want to get rid of z's. Okay, so let me pair the first and the third one now together. You cannot change and say, well, it's easier to get rid of the y's, for example. Let's say, you see right in here, right in here, you see the y's. Those are easier to eliminate, but since we decided on eliminating z, we have to stay with that. So x plus y plus z equals 4, and in the third equation now, the third one, this is 2x -y -2z equal to -1. You see how easy it is to eliminate the y here, but still we have to eliminate the z. So all I need is to multiply 2, because right in here we want to get opposite there. Okay, opposite of -2z is 2z, so that's why I'm multiplying the first equation by 2. And when I do the first equation, it's going to become, that's going to be 2x plus 2y plus 2z equals to 8. And the second equation is 2x -y -2z equals -1. And there you have that. Okay, and add the two equations together. This becomes 4x plus y equals 7. And there I have an equation in just x and y. And remember, up here I had an equation in x and y. So look at this one and look at this one. Both of those have the same variables, unknown variables, x, y. So what I do next now is I'm going to pair them together. This is like a whole new system now we need to solve. 2x -y equals 5. How you solve this is up to you, and the easier method here is elimination. I'm going to stay with elimination method. And again, the y's are already opposite, so I'm just going to stay with those. And let's just add the two together. Okay, that's all I'm going to do. Add two equations together. And when we do, indeed, these add to 0. So I have 6x equals 12, divide by 6, and that solves for x. So x is 2. Therefore, we're able to solve for one of the unknowns. Now, what I need to do is I need to back substitute for x into the other equations, and this is going to be 4 times 2 plus y equals 7. You can also substitute for x in here, because again, this is a system. That means the solution must work in all of them. So in fact, that's how we verify if a proposed solution is a working solution in a system. You just plug them in for the variables, see if they work. So let's finish this off. And 4 by 2, 8 plus y 7, subtract 8, you get -1. And there you have it. So We found the solution to x and y. All we need is a solution to z, right? I'm going to go to the first equation. Again, you can go to any one of these, all three of them. You can go to either of those and solve for x. But the easiest one, I think, is the first one, isn't it? So let's go x, y, z adds to 4. First equation, x plus y plus z equals 4. X is 2, y is -1, plus z is 4. And that means z is equal to 2 minus 1 is 1. Subtract 1 from both sides, we get 3. And there you go, we have the solution in the form of ordered per x, y, ordered, actually not pair, sorry. This is now an ordered triple x, y, z, and the solution is going to be 2, -1, and 3. That's how the solution is written. Okay. And 2, -1, 3, is that what we had earlier? 2, -1, 3. Yes, we did, right up here. You see that? We have 2, -1, 3 here also. So it's the same solution again. It's like going home, either you take the surface roads or you can take the freeway. Both ways you get home. So that's how these two methods are. And there you go. With that, we are done with this lecture, and we are done with section 8.4.